So this is the session 4 of the module 5b, which is related to the masonry buildings are concerned, and in this today's sessions we'll see about the lateral load analysis, how the lateral load is to be calculated for the masonry structures are concerned. To understand the proper design procedure for the low-rise masonry buildings, so this particular procedure is divided into several steps. In actual practice, these various steps may not be so clearly delineated and so distinctly separated, but at this stage at least this step-by-step procedure is recommended in order to understand it properly. So here in the figure it shows that masonry building is subjected to lateral load and its resisting mechanism. In load bearing masonry buildings, the walls which carries the lateral loads also act as a shear walls to resist the lateral load. The structure's wall parallel to lateral force and subjected to in-plane shear force and bending are called as a shear walls. The walls perpendicular to the seismic force or a lateral force and subjected to out of plane bending are called as flexure wall. So in the figure we can see both the flexure wall as well as the shear wall. So shear wall will resist the total lateral force, whereas the flexure wall will check for the lateral force, and whatever the diaphragm action will be there, that is the distribution of lateral force depending upon the rigidity of the structures will be there. So here we can see the different steps to be followed for the lateral load analysis of masonry buildings is concerned. The first one is determination of lateral load based on the IS code 1893 part 1, and step 2 is distribution of lateral forces on the basis of flexibility of the diaphragms, and step 3 is determination of rigidity of shear walls by considering the openings, and then step 4 is determination of direct forces and the direct shear force and the torsional shear forces in the shear walls, and step 5 is determination of increase in the axial load in the PS due to overturning, and step 6 is check the stability of flexure wall for out of plane is concerned. So now let us go into detail about how this lateral loads is to be determined. So in case of the earthquake load, it is one of the most important as far as the lateral load on a structure due to the earthquakes are concerned. So in which arises from the lateral load is because of the inertia masses of the structure, and these earthquake loads are sudden and the dynamic and can be immense intensity. So the magnitude of lateral force mainly depending upon the seismic zone, type of the soil, ground acceleration, then ground conditions, fundamental the characteristics. The design base shear shall be first be complicated as a whole and then distributed along the height of the building based on the simple formulas appropriate for the buildings with regular distribution of mass and stiffnesses. The diagonal force obtained at each floor level shall be then be distributed to the individual lateral load resisting element depending upon the floor diaphragm actions. And here the following are the major steps. The first one is determination of the base shear, and next one is vertical distributions of the base shear to the different floors. So let us see that how this the base shear is to be calculated. So here the design base shear is denoted as VB, and which acts at the building in a given directions, like VB is equal to alpha times of W, where alpha H is the nothing but the horizontal seismic coefficient of the structure, which is determined by the expression Z by 2 into I by R into SA by G, where this is applicable for when the time period is less than 0.1 second, and also alpha H is will not be taken as less than Z by 2 wherever the whatever the value of the I bar R ratios is concerned. So now the how this vertical distribution of the base shear to the different floor levels are to be taken place. So here figure 2 shows the design base shear computed and shall be distributed to the various heights of the building. So here the expression is that Qi, how this distribution is to be done is that Qi is equal to Vb times Wi into Hi square into sum of Wi into Hi square. So in this figure we can see the first one is the seismic shear on the building, second one is this, how this seismic load is going to happen and how this story shear is to be calculated at every story levels. So here in this case Qi is nothing but the design lateral forces at every floor ith level, and Wi is the seismic weight at the floor I, and Hi is the height of floor I measured from the base, whereas N is nothing but number of stories in the building, and E is the number of levels at which the masses are located. So let us take one example where we can see that lateral forces is to be determined for the two-story unreinforced brick masonry which is situated in Roorkee. And here are the some building datas are there. The plan size is 20 meter by 20 meter. The total height of the building is 6 meter. Each story is of 3 meters. Then weight of the roof is taken as 2.5 kilonewton per meter square. Weight of the wall is taken as 5 kilonewton per meter square, whereas live load at the roof is taken as 0. Then live load at the individual floor is 1 kilonewton per meter square. So here live load of that is 25% only is to be taken, because here the live load is less than 3 kilonewton per meter square as per the 1893 codal provisions. Now here the zone factor Z is taken as 0.24. And also important factor of the building is 1. Now the response reduction factor here it is taken as 1.5, and the whatever the spectral acceleration which is SA by G is taken as 2.5, and the soil condition is type 2 medium soil is there. Now the figure itself shows that the two-story masonry building of height 3 meter individuals, and the in plan you can see it 20 meter by 20 meter is there, and another figure is showing the 780 is the base shear, how it is to be calculated. We will see it into the following steps, and how the distribution of the lateral forces 206.26 kilonewton as well as 573.74 73.74 kilonewton, how it is to be calculated, followed by these steps. So here in this calculation we can see the seismic dead load at the roof level. First we can see it. Next here the weight of the roof is calculated as 2.5 is the weight, and it is happening in 20 meter by 20 meter plan, so that's why weight of the roof is 1000 kilonewton. Then weight of the wall, so here it is taken as 3 meter height wall is there, and the loading is 5 into 4 walls are there. So now it is the half of the wall is to be taken because it is at the roof level, so that's why it is calculated as 600 kilonewton. And the weight of the roof, the whatever the level is there, so now it will be weight of the roof plus weight of the wall, so it is to be calculated as 1600 kilonewton. Now the seismic dead weight at the second story is to be calculated as weight of the second floor is 2.5, that is the load is there on acting on a 20 meter by 20 meter, that's why it is 1000 kilonewton. And weight of the wall, that is the above and below 3 meter height is to be taken, that's why it is 5 times of 4 into 20 by 3. 3 is the height of the wall is there, so that is works to 1200 kilonewton. Then the weight of the live load, so here taken as a live load as a 1, and that is also 25% reduction is made, and the floor area is 20 by 20 meters, so that's why it is 100 kilonewton. Now the total weight on the second floor is taken as 1000 plus 1200 plus 100, so total is 2300 kilonewton. Now the total weight of the building is taken as 1600 plus 2300, that is total weight is 3900 kilonewton. Then according to the natural period as per the IS 1893 is taken as d is equal to 0.09 h divided by square root of d, where h is the total height of the building and d is the one side of the building, that is 20 meter. So here it is taken as 0.12, and based on that we can calculate SA by G as 2.5. So now the base shear, how it is to be calculated, the base shear VB is equal to AH into W, whereas AH is nothing but Z by 2 into I bar into SA by G into total weight W. So if you substitute Z as 0.24, I as 1 and R as 1.5 and SA by G is 2.5 and weight is 3900, the base shear is calculated as 780 kilonewton. Now this 780 is to be distributed at various levels. One is at roof level, another one is at the story level. So this 780 is to be distributed based on the weight and height WHI square divided to WHI square plus W floor of the other story. So according to that it is calculated as 573.74. Then similarly for the second floor level also this 780 is to be WHI square divided by sum of WHI square. So now according to this it is calculated as 2206.26, which we can see it from the figure. So this 780 at the bottom is to be distributed as 206.26 and 573.74. So like that the total load is to be calculated. Now this step 2 is nothing but distribution of lateral forces. So here figure shows that distribution, how the lateral forces in a box type of shear wall buildings are to be done. So in order to transfer the seismic forces to the ground, there should be a continuous load path in the building. The general load path is to be taken as the earthquake forces, which originates in all the elements of the building and are delivered through the transverse walls of the building and is bent between the floors. Whatever the lateral loads are there, so they are transmitted from these transverse walls to the side of shear wall by horizontal floor and roof diaphragms. Whatever the diaphragms distribute these forces to the vertical resisting components such as shear walls and vertical resisting elements if any, then which transfer the force into the foundation. Then diaphragms must have adequate stiffnesses and strength to transmit these forces. The distribution of lateral forces in the masonry wall will depending on the flexibility on the horizontal diaphragm, that is how rigid the walls are as compared to the rigidity of the diaphragms. Then the rigidity of the diaphragm is classified into two types. One is flexible, another one is the rigid one. So that is rigid and flexible diaphragms are there. So here we can see both the figures that how this rigid and flexible diaphragms are there. So here whatever the roof level is there, it is act as a diaphragms, and whereas the at story level, first story level, second story level, vertical wall will be act as shear walls. So like that we can identify the lateral force distributions in the box type building and box type masonry building subjected to lateral load, and whatever the bend in the first story or second story transverse to the walls, and also distributions of the forces in second story and distributions of forces in the first story. So what this figure we can get it. Next one is the whatever the determination of the rigidity of the shear walls is concerned. So here whatever the lateral load is there, so that capacity of the shear wall is mainly depending upon the in plane resistance rather than the out plane stiffnesses. Whatever the distribution of the lateral load to the shear wall is based on the relatively wall rigidities. If the rigid diaphragm supports the wall and the segment of the wall directly equally the effects, and then the rigidity of the shear wall is depending on its dimensions, modulus of elasticity, modulus of rigidity, and the support conditions. So here in this figure we can see the peer analysis. So in this peer analysis, if the masonry structures, it is generally assumed that it is one or two story building. Then wall may be considered as cantilever segment of the walls between the adjacent openings, and they are called as a piers and might be considered fixed at the top and bottom depending upon the relative rigidity of the walls versus the those of floor diameters. Then this the figure itself will convey the how this cantilever from the fixed bottom and how the deflection of wall due to the bending and shear is concerned. So next part is step 4. So there it is nothing but the determination of the direct shear forces and torsional shear forces are concerned. So now in case of the direct shear forces is concerned, so the whatever the rigid the diaphragm is there, it is assumed that the walls are tied together with the diaphragm and the lateral force will be distributed to the walls in proportional to their relative stiffnesses. Now here as per as the figure you can notice that how this torsional shear forces are to be noted. So here when the center of the mass and center of the rigidity do not coincide, then the torsional shear force will be induced on the walls in addition to the direct shear force. So here in the figure, so we can see the horizontal load P which will be at the center of the mass, and then the torsional moment MT is indicated is equal to Py into Ex, where Ex is equal to the distance between the line of force, that is the center of mass, and the center of rigidity. Even in symmetrical structures, whatever the eccentricity E is equal to 0, the minimum eccentricity is accounted as 5% of the building dimension and is assumed as the accidental eccentricity. So which we can see it from this figure. Next one is the determination of the increase in axial load due to overturning. So here in shear walls, the whatever the principal forces are there in plane shear, that is the direct and torsional, in plane moment in plane shear and the half of the height of the pier is there, and the dead load and live loads carried by the pier. Then in addition to these forces, sometimes the lateral forces from the winds or earthquakes create a severe overturning on the building. If the overturning moment is great enough, then it will, what will happen, it will overcome the dead weight of the structures and any cause of tension at the end of the pier wall, which we can see it from this the figure, how this axial load which of the pier is happening in because of the overturning action is concerned. Now next step is the wall subjected to out of plane bending. So here in the seismic design of masonry building, it is assumed that the total base shear induced by an earthquake will be registered by in plane shear wall and transverse wall or the flexure wall, which will not register any shear. However, the flexure wall will be checked for out of plane forces with the vertical load. So this action produces combined action of axial compression and bending forces. Laterally, the stability of wall needs to be checked for this combined effect. The whatever the relations between the combined effect, so in the figure you can see the axial load P and bending moment M can be related to the virtual eccentricity as E is equal to M by P. And for linear elastic beaver, the section is to be expressed as Fm is equal to P by A plus M by S. So here Fm is nothing but a limiting or a allowable stresses for the combined axial compression and bending, where A is the cross sectional area and S is the section modulus. So what we can see it in the figure. So these are all about the various steps to calculate the lateral load analysis is concerned.